Okay, let's get started. Are there any questions from last time about the material or what? So I see that there's not much participation on Piazza, and by not much, I mean none. So what do you think I'm going to recommend to you? Post on Piazza. What do you post on Piazza? Questions. So if you don't have any questions now on the homework, where should you ask questions? Piazza. Because I'm going to guarantee you, as you're going to be doing the problems, you're going to get stuck. Unless you're just absolutely brilliant at this, which is the very minority of people, please ask questions if you're not 100% certain about something. Okay? But anyway, are there any questions about what we did last time? Okay, so what did we talk about last time? Yeah, so union and what else? Concatenation and star. And okay, what are those three? Regular operations. Did we talk about any other operations? Complement. So did we? I remember proving some things in class. What did we prove? We proved union, that you can get a bunch of workers together under a union. Is that what we proved? Regular languages are closed under union. And what was the name of the construction used in it? Product construction. Why is it called product?
It was a Cartesian product.
Cartesian product of what? What part of the machines? The states. Cartesian product of states. What else did we prove?
Intersection.
Well, we did intersection, but to get intersection, what did we need to do first? The complement, right. And what did we do in that proof? What did we do to the DFA to get the complement one? Yeah, we flipped the final and non-final states. Cool. So did we prove that regular languages are closed under the regular operations? Because the word regular is the same, right? So therefore it's true. No. Which ones did we not prove? Concatenation and star. All right. What is concatenation of two languages? So if I have two languages, A and B, what is the concatenation of the two? Yeah, WX such that W is in A and X is in B. Is it equal to, actually I won't go into that. We'll get to that when we get there. So that's concatenation. So let's just prove it right now that regular languages are closed under a concat. You take the two DFAs, run the DFA on the first DFA on the first part of the string, second DFA on the second part of the string, and accept if both pieces say yes. Are we done? Run the first DFA on the first part, and then the second DFA on the second part, and then we're done. What's wrong with that idea? Oh, actually, that is true. We don't know the length, but because we can only see the next character ahead. But more importantly, what else is wrong with that?
Oh, we don't know where to split.
Right. We don't know where to split. Do I split after the empty string and the rest of the string as the second part, or one character in the rest, two characters in the rest? Or any of those combinations might work. It might be that some multiple of those combinations work, and I don't know which one to use. So I mentioned last time that if we can guess where to actually make the switch over to the second part without consuming any characters, so read some part of the string and then magically guess your way over to the second part without having consumed any characters, I think we can actually do it at that point. But do DFAs have a way of guessing whether to do a transition or to have a transition that doesn't read anything? We don't have that possibility. So let's actually talk about a generalization of DFAs, where we have the ability to have these instantaneous switches of applying a transition without actually reading any characters at all. But we also might as well generalize to say we could have multiple transitions out of the same state with the same symbol. We might as well allow that possibility because DFAs didn't allow that before. So let's talk about NFAs, which are non-deterministic. Finite automaton, NFA. So this NFA is also a 5-tuple with the 5 usual suspects. So it's got states, input alphabet, transition function, start state, and final states. Same as before. Well, I think we should keep the states part exactly the same. We want to have it be a state-based machine. We want to keep input alphabet working the same way as before. Start state, we only really need to have changes on the transition function itself. We don't need anything else to change to accommodate concatenation. So what we'll do is we'll say that the other 4 pieces are the same. So the states, the input alphabet, the start state, and final states are as for a DFA. So these 4 pieces are identical. So finite set of states, input alphabet, start state, final states. Same as before. But we have that the transition function does something else. So let's actually look at an example of what these NFAs might look like. Well, we need to allow for multiple transitions on the same symbol out of the same state. So we got to handle that possibility. But we also need to have transitions of a special type where we say you don't read anything when going over this transition. All the ones we've looked at so far, you consume a character, but here we're not going to actually consume a character. So what type of transition, what type of symbol do you want on the transition to indicate we're not reading anything at all? What would make sense? Yeah, epsilon, the empty string. So we're going to have something along that line. So let's do an example first. So let's do this. Okay, so here is an example of an NFA. So what makes this not a DFA? What changed between the... I thought it said, hey Siri again. What makes this not a DFA? What changed?
Transition.
Well, yeah, the transitions, but specifically what transitions?
Epsilon.
The epsilon, obviously, the transition there, so that thing changed. What else changed?
Q1.
Q1 has no 0 transitions. Yes, exactly. There are no transitions with 0 coming out of Q1. In fact, there are no transitions labeled 1 coming out of Q0 either. But what else changed? Right, Q2 has 2 transitions that are both labeled 0. So we need to be able to handle all of these possibilities. And why is that? Because how would we do concatenation? So let's just look at a typical example of a DFA. Well, these could be DFAs, NFAs, it doesn't matter. So let's just assume it's a DFA. So what we're going to show right here is that we can make an NFA for the concatenation. Not necessarily to show that regular languages are closed under concatenation, but we can make an NFA for the concatenation. So let's just say that we have DFA1 over here and DFA2 over here. They can be NFAs, but it doesn't matter. Each of them has a start state, and let's just say, just for example purposes, DFA1 has 2 final states, and DFA2 has 3 final states. Well, how can I instantaneously say DFA1 has accepted the first part of the string, and then now I want the second DFA to run on the second half of the string? But keep in mind, when I'm done reading the first part of the string, I don't want to read any characters to switch over to the second DFA. So what would we do here? Epsilon transitions, but from what to what? That's the key. Well, let's see. I want them to certainly be in the final states of the first DFA, right? Because I want the first DFA to say yes on the first part of the string. And the only way it says yes is if it's in a final state. And then I want to switch over without reading any characters. Well, what would that be here? An epsilon transition, but to where? The start state of the second DFA. Right. So then I would have a transition like this, which is an epsilon transition. I know we haven't finished the definition. We'll get there. There's one thing that's wrong about this diagram, though. What is it? And it's something to do with the first DFA.
There's final states.
Well, could it be the case that DFA1 reads the entire string, ends in one of its final states, and just declares accept because it's read the entire input? Could that happen? Yeah, it could be that the split is the entire string is the first half and empty string is the second half. So we could just quit early, possibly, if we end in one of the final states of the first one. So how do we mitigate this to say you must run through the first machine and the second machine all the way through? What would we do here?
Remove the final state.
Remove the final states of the first one. Yes. So if there's any chance of accepting, the only way we can do that is going through both machines. So that is what non-determinism actually means. Non-determinism means, and I know this may sound weird, but it means that if there is any chance at all of going to an accept state, if you take a certain transition, you will take that transition. Okay? So, for example, let's just say that we have, for this example, NFA right here. Let's just say we're only looking at the empty string as input, so just no characters. Well, if we enter at Q0, is there a transition that I can take that will guarantee me acceptance at some point? If I just have the empty string as input, and I'm at Q0, yeah, what transition is that? Going to Q1. So am I forced to take that transition, though? No, I don't have to take that transition because I've read all the input already. So NFAs actually give us choice. We don't have to take transitions always. If I want to accept, I have to read the entire input, just like a DFA does. But I don't have to take certain transitions if I have a choice. Okay? So in this case, I would have a choice. I could either stay in Q0, or I can take the thing over to Q1 and then accept. If there is a way for me at all to accept, I will take it, which in this case we do. So let's actually do the formal definition of the transition function. Well, what we have here is that we do have a state. So we're always looking at a previous state and then looking at transitions that could occur. Well, what could appear on the transition labels here? What things could appear? Well, can something from the input alphabet appear? Yeah, so and what was the name of the input alphabet? It starts with sig and ends with ma. Sigma, right. But what else could be on the transition label? Yeah, epsilon, right. But so that takes care of the epsilon transitions. What is the other thing that we need to handle? Well, we handle states, but actually you're correct. We could have multiple states that we could go to. Could we have 0 states that we go to? So like there's no transition on a certain symbol. Could we have that?
Yes.
Yeah. What's an example here in the NFA we have here? Yeah, not Q2. Well, I guess you're right. Q2 on epsilon doesn't go anywhere. But say Q1 doesn't have a symbol, a transition with symbol 0 on it. But could I go potentially to all states on a certain symbol? Like, could I say Q1 on input 1 goes to all 3 states? Yeah, I could do that if I wanted to. Could I go to any subset of states, including the empty set of states? Meaning I go to no states at all. Yeah, I can certainly do that. So let's actually figure out what this transition function looks like. Well, we have a state, and how do I write that in terms of a function? It comes from the set of states, which is called, should be more emphatic. What is the set of states called? Q. Cool. Q, great. Well, the transition function takes 2 arguments. The second one is the thing that can appear on the transition labels. Well, what can appear again on the transition labels? It could either be something from the input alphabet sigma or epsilon. Well, how can I include epsilon into a set? So sigma is a set, remember? How can I include epsilon into a set? Union, right. So then what I do here is I take sigma and I union it with, can I say epsilon like this? Oops. Something like this? Can I say that? No, what? Why is this not good? It's not a set. How do I make it a set? Put a curly boy on top of it. All right, so now my handwriting is going to get even worse. So curly brackets on there. We have like 3 symbols that look like E's in here, so manage while you can. So that's fine. But what should the transition function output here? Should we output exactly 1 state like a DFA does? No. What should we output here? Well, it could be any subset of the states. So in general, just a set of states. Well, but remember, what has to go here is I take something from there, and that's the result of the function. So like with DFAs, we put the set of states there, I pick 1 state from there, and that is the output of the transition function. But I want to output a whole set of states, a whole subset in essence.
The power set of Q.
You let the punchline go too early. So what is the set of all subsets of something? What do we usually call the thing that has all possible subsets of something?
Star set?
Not star. The power set of something. So we're going to go to the power set of Q. Sometimes the notation 2 to the power Q is used. We're going to use the scripty P thing. So scripty P, all it means is that that's just all possible subsets of the set of states are there. and we can go to any one of them we want. Whereas with a DFA, we just pick one state that we can go to. Here, we pick one set of states we can go to. Yeah.
Where do you get the 2 from on that, or it's always a 2?
The 2 here is just notation that I've seen before. So some sections, including the one that I took a long time ago, the 2 is used for Powerset. So they mean exactly the same thing.
Like Powerset be 2 to 8,
No. So the notation, it's just notation.
Yeah.
And 2 to the thing in the X.
Like the B would be where the Q is on that too.
No, the P is just the function name. The thing that goes up here, upstairs, is the set you want to take the power set of.
Yeah. What I'm saying is the 2 like constant like with that always, or is that number?
It's just notation. It doesn't actually mean anything, which is why I like the scripty P better anyway. It's just notation. Other questions? Okay, so let's just do one example from this NFA we have here. So let's just look at delta of, let's see, Q1 on 0. Well, for NFA land, what is the output of the transition function always? Structurally, what is it? Is it a single state or a whole set of states? It's a set of states. So whatever I put here as the output of going from Q1 on input 0 must be a set always. Well, does Q1 have a transition on 0? No, so what is the set of states here? The null set, empty set, same thing. Yep, cool beans. What about, let's do one more so that we get something other than empty. What about Q2 on input 0? In other words, what are all the states I can reach from seeing zeros? Just a single 0, sorry. Well, from the diagram we have a transition that goes up to Q0 and one that goes to Q1. So what is the set of states here? Yeah, the set which has Q0 and Q1 in it. In other words, the states I can reach. What about Q0, comma 0? What is the set of states there? From Q0 only reading 1, 0. That's actually a better answer than you may think. Let's do that one. Q0 reading a 0. What is that set? State your answer again. Q1 and Q2. So that's the answer that was given. Does everyone agree with that?
I would have guessed just Q2.
You would have just guessed Q2. Why is it just Q2?
There's only one transition.
We're only looking at the transitions labeled 0. Okay? So we don't include the epsilon in the transition, even though we're not actually reading a symbol. So here, it's just Q2. But I say that your answer is better than you may think because we're going to actually use that in a few minutes. Cool. So any questions on what the transition function does? And we could define computation and accepting computation. There's a slight difference here in that some of the transitions we can take are epsilon transitions, and at some points we may have a choice. So could an NFA have many, many computations on the same string? Yeah, because there are choices we can make. Could an NFA have 0 computations on the same string? Meaning, like, there's no way that you could read the whole string. Here's an example. It's kind of a dumb example, but it shows the point clearly. How many computations are there on input 0? Just a single 0. Ooh, way more than 1. Infinite. Why? Right, I can just do the epsilon transition as many times as I like, and then at some point later do the 0. You may think that's kind of dumb, but am I allowed to do that? Yeah. What about the number of computations on input 0, 0? Can I read the whole string? No. So are there any computations? Remember, computation means we read the entire string. Okay? So can I read all of 0, 0 here? No. If I did this, is there 1? Yeah, so we can read the whole string this way. So we could have infinitely many computations and or 0, or some number in between. Okay. Yeah.
So in this case, since we have a transition that the label is the empty string, that means that we have a choice between that epsilon and any other input possible at that state?
Yeah, so I'm actually never forced to do a transition. Okay?
Even if there's no epsilon?
Yeah, even if there's no epsilon, I'm not actually forced to do a transition unless there's exactly one choice I can make. In that case, if we do remove the epsilon transition, then yeah, then we're forced to. But let's just say I have input 0. I don't have to take that epsilon transition if I don't want to.
So is it like a wildcard kind of thing where the epsilon I could take, the input, just keep it there?
Yeah, so that's actually a good analogy that epsilon just means whatever's the next character in the input, or even if there isn't one, we can take that transition. So it's like a wild card. I like that analogy. Other questions? Okay, so what does this construction just show us right here? Does it show us or prove that regular languages are closed under concatenation? Be careful. Does it show that regular languages are closed under concatenation? No, why not? Could it be the case right now, although we'll prove that this is false, could it be the case that NFAs could recognize a non-regular language with this extra power? It'll turn out to not be true, but have we proved that yet? No. So we can't conclude from this that regular languages are closed under concatenation. Can we conclude, though, that the languages of NFAs are closed under concatenation? Yeah, because I can just stick an NFA both parts right here, and I just made an NFA for the concatenation. So be careful about statements like this. Before we prove equivalences, be careful about showing closure like this. Okay, well, we certainly, if they are the same as regular languages, we're done right here. But we're not there yet. So we did concatenation. What about union for NFAs? Well, let's see. So let's look at union for a second. So let's just say we have our D or NFA. It actually doesn't matter here because we're just going to make an NFA anyway. And let's just say it has some final states. This is NFA 1, NFA 2 down here. Well, how could I make an NFA for the union of these two? So remember, what does non-determinism mean? It says, if I have choices of what transition to apply, if there is some way of applying a certain transition that guarantees me to accept at some point in the future, I will take that transition. So it's like you're looking way far ahead in the computation and you know, I'm going to accept at some point. And so that's what non-determinism gives you. Well, how can I exploit that for union though? Okay, well, I don't know, given the string that I have, whether the first NFA is going to accept it or whether the second one's going to accept it. Could the non-determinism help me here? Yeah, how can it help me? Well, couldn't I just guess which of the two pieces it is? Let's try that. So maybe let's make a new start state and then guess our way into the first machine or into the other machine. What is this notion of guess for non-determinism? Epsilon transitions. Because I don't want to have to read anything before the NFAs here have a chance of looking at the string. So we better do epsilon transitions here. Then epsilon down here. Does this really get union, though? I claim it does. Why does it?
Because you either get the output from one or the other.
Yeah.
Depends on the first guess.
Right. So if the first NFA has a computation that accepts the string, do I have a computation that accepts the string for this bigger NFA? Well, yeah, I just tack on the first state, the new start state, onto the computation, and then just put the epsilon transition on the front. Same thing with the second NFA. So, in fact, we get union really easily. Did we get all the regular operations this way? Ooh, we didn't get star yet. So let's do star. What is informally, what does star mean? So if I have a language A, a set of strings A, and I look at the star of the A, informally, what does that mean? I said informally. Yeah, so I want this to be as simple as possible. Let's try to not resort to the formal definition if we don't need to. Informally, what does this mean?
Combine 0 or more letters.
Yeah, I'm going to amend your answer a little bit. So is 0 or more strings from this set? Yeah, so concatenate 0 or more strings for from A. So just pick some number you want, any positive number or 0, and then pick a string from A, and then each that number of times, and then concatenate all of them together. Well, let's just say that we have an NFA right here. It has a start state and some final states here. And let's just say this NFA has that language, A. It accepts those strings A. Well, how do I get the star of A here? Meaning that I can go through the machine, the NFA here, and then when I'm done, meaning I accept, I can restart the computation, read some more, go back, read some more, go back, read some more, as many times as I like. Okay? How would I do that here?
Epsilon from final to start.
Right. So that seems like a good idea, meaning that there's something to amend to it. But it's a good start. So let's go from the final states to the start state here with epsilon transitions. So this seems to do what we want, right? We can go through the whole machine and then do epsilon transitions back to the front, and then read some more, go back, read some more, go back, read some more. And the only way we can accept is if, first off, each time we went through the machine, we ended in a final state, meaning we just read something that the machine does accept. But then if we want to go back, we just follow the epsilon transition, and we're not reading anything on it. What's the issue with this?
The length is also
The length is, well, there could be characters in the middle, so each time I go through, I may be doing something else.
start state has to be final and the final states have to be non-final.
Second part of that, I'm not sure is true, but the first part certainly. So one of the problems of making pictures like this is that it gives you a false sense of what is actually true. Could the start state be final? Yeah. Could all the states be non-final? Possibly. Yeah. So this is just to give you an idea. This is not like what actually happens in reality. So what happens is that what string is in the star of any language at all? Yeah, epsilon. Meaning what has to be true of the start state? It has to be final. So if we make this guy final, we should be good, right? What's the issue with this? Suppose we had a situation like this. So let's blow this up a little bit. Suppose we had the start state here that's now final. We had a transition on a certain symbol, and it comes back like this. And let's just say neither of the two states has another transition on input A. Well, and let's just say before we made it final, there's no way to accept AA. So if I read AA, then I come back to the start state. Well, what do we do now if I put that guy to be final? I accept it. Did I just change the language of the machine? Yeah. So we don't actually want to do this. We do want something, though. We want some state that's reachable from the start state to be final, for sure, because we need to get the empty string for the star. So how can we amend this?
New start state, that's the final state.
Great idea. So let's make a brand new start state out here that is final. Brand new start state. Well, what do we do now with this brand new start state?
Epsilon transition.
Epsilon transition your way into the old start state. Cool. So does everyone understand why we actually needed to do that? Let me ask you a question. What if, for example, there's no issue like the thing in the blue right here where we have this AA situation? What if I could just freely make the original start state final and it doesn't change anything? What's the advantage of doing it this way, the way that we have amended it? It always works. Because if I need to look at the NFA, then I need to be clever about, do I actually need to put the original start state to be final? Whereas this approach, I don't care what the NFA actually looks like. I don't need to do any thought about this. So can a computer do this? Yes. So we don't need to do anything clever at all, which is awesome. Okay, but are there any questions about star and how we actually did this? Yeah. Mm-hmm.
After we created the new start state, why did we keep the epsilon states to the original first state and not to the...
A great question. So remember that epsilon transitions are optional. You do not have to take them because they're like wildcard transitions. So let's just say that we are currently at this state right here, the one that I put in arrowed in green. That is a final state, for sure is a final state. And let's just say that I'm not going to read any more after this. So we're completely done reading the input. Do I have a way of accepting from that state? Yeah, what do I do? I stay there. So what if I do have more to read? I definitely have more to read and I want to accept. What do I have to do in that case? I have to take the epsilon transition. So the reason why we did this is that we needed a way to get back through the machine. However, consider this. Suppose that I instead did this instead. I epsilon my way over to the new start state. Is this let's just say I cut out the other ones. Is that a problem? No. Why is it not a problem?
Because you can always take the epsilon again.
Right, I can always take the epsilon one back in. But hold on for a second. The epsilon transition goes to a final state, the new start state. Is that a problem? Because hold on. If I have a non-final state going to a now final state, whereas if it went to a non-final before, that could change the language. But is that a problem here, where a final state goes to a final state? No, because again, I don't have to take the epsilon transitions if I don't want to, okay? So that you could either do the one in red or you can do the one in purple. It actually doesn't make a difference. But we actually do need to have a new start state. That is required because in some cases you really do need it. Other questions? Okay. What do we want to, so what have we shown about the languages of NFAs? What are they closed under now? Union, concatenation, and star. Cool. So we just proved that. What do we want to prove? The regular languages are closed under those three things. Do we have those three already for regular languages? No, we don't have it. That sounds like a problem. Can anyone suggest a solution or an approach to bridge that gap?
Way to convert NFAs to DFAs.
Oh, if we have a way to convert an NFA to a DFA, are we done? Yeah, because every DFA already is an NFA because I don't have to have epsilon transitions or multiple transitions on the same symbol. But if I can convert an NFA to a DFA, that's enough. Because I can just do this construction, where are they? The union, the star, and the concatenation constructions, and then apply whatever conversion we need to get the DFA we actually want. Sound like a plan? I need more enthusiasm. Sound like a plan?
Yes.
Yeah. I guess I need to adjust my tone. All right. So what are we going to do? So let's actually do an example first before we get to the formal stuff. Because the formal stuff we'll need an example for. So let's look at our example again. And I'm going to delete these unnecessary transitions to make it cleaner. Cool. So we have an NFA right here. Let's just say that we're going to look at the string 1, 0. Okay, so we have a string 1, 0. Here's another thing about NFAs. NFAs, so if you have taken other instructors here, they may say that non-determinism is just massive parallelism. We're simulating many transitions at the exact same time. Is that what non-determinism does? What non-determinism does is it always makes exactly one choice. If it has many choices to make, it makes one of them. It doesn't simulate all of them in parallel. But for a deterministic machine, what would it have to do? It doesn't know what choice to make. So what should it do? It must do the parallel simulation. Okay? Well, does the NFA, from a non-deterministic point of view, does this NFA accept 1, 0? Is there a way for me to get to Q1 on input 1, 0? How would I do it? Oh, so I apply the epsilon transition at the beginning, Then I apply the one transition down to Q2. And well, in Q2, I have two choices on input 0, but I choose the one that goes to Q1. Okay, fair enough? Well, let's see. So before the computation begins, we can be in what state? Q0, right? Where else can we reach without reading a single character? Q1. So I'm going to include it on our list here. And what we're going to do, at least a little bit, is do a deterministic search. So kind of like a breadth first search in a sense, of what we can do at each point, and then figure out, okay, is there a way for me to accept? Okay, great. So let's look at Q0 here. Where can I reach from Q0, just Q0, on input 1? Nowhere. So this goes to empty set. So in some sense, this branch of computation is closed off. I can't continue along that way because I don't have a choice anymore. Cool. What about Q1? Where can I go from Q1 on input 1 to Q2? So I put Q2 here. Is there anywhere else that we can reach from either empty set or Q2 without reading any characters? Is there anything else we can reach? No, because empty set doesn't correspond to a state at all. Q2 doesn't have any epsilon transitions coming out of it, so we're done so far. Well, the empty set thing, we're done with that, so we don't have to worry about that anymore. What about Q2 now on input 0? Where could we go? Well, I could take the Q0 route or the Q1 route. So here, I have two choices I can make. I could either do the Q1 route or the Q0 route. Is there anywhere else other than these two states that we can reach without reading anything? Well, the Q0 does have an epsilon transition to Q0, but we already have Q1 on our list, so we're good there. Could I reach Q2 via epsilon transition? No. Well, are we done reading the input at this point? Yeah. Is there any path from the states on the left to the states on the right that landed in a final state? Yeah, namely this one right here. So namely this path got me to Q1 and got me to accept. Well, actually, it should be include this one because we went from Q0 to Q1. So it's really this path that we took. So as long as there's one way to accept, do I care about all the other ways that I could have taken a choice? No. As long as there is one way we could accept, we're okay. All right? So I don't care about the that it ended in Q0 as another way we could have went. I just care about, is there some way for us to eventually accept? So let's actually make this more formal after the break. Okay, let's start up again. Are there any questions from the first half? Guys, shh. Okay, so what does non-determinism actually mean? It means that if we have choices that we can make, we could make any one of those choices. But what non-determinism does, it says, oh, if I make this choice right here, and I know that it'll eventually lead me to go to a final state and accept, I will make that choice. Okay? So it's not like we can just make any choice and it simulates all possible choices. It doesn't actually do that. It makes exactly one choice. Okay? So, yeah, go ahead.
How would you do that without knowing the whole string at once?
So that's what is so magical about non-determinism. It doesn't actually know what the string is, but it can know whether it's going to accept or not. Yeah. I love that you just went like, okay, yeah, this magical computation, it's fine. So you can never implement a non-deterministic device in the real world, right? Because you need to know the input before you've actually seen it. So why do we even care about this? Is it just because it's in the textbook and I just teach it to you and like, yep? No, it's because it allows us to accomplish these problems of concatenation, union, and star, which are about, I have this problem I want to solve, and it's composed of multiple pieces that we stick together. The model that we want to work with is the DFA model. We definitely want to work with that. But so we know how to do union with DFAs, and that's the product construction. But the problem is with concatenation and star. It's really hard to do concatenation with DFAs directly. Whereas we're computer scientists. We resort to indirection all the time. We indirectly solve this problem in another domain, and then we port it back if we need to. So that's why we made this NFA model, to make the problem solving far easier, and then we can just focus on the conversion back to make the process complete. So if you want to make a DFA for composing multiple pieces together, like some part is for example, the HTTP header, and the second part is for validating user input or something. You want to break this up into multiple pieces, but you want to use it in a deterministic finite automaton setting. So you want to break this up into concatenation because the bytes that are sent to you are just this one long string, and the first part appears here, second part appears here. And you want to be able to switch over when you need to. But you can't do that directly with DFAs. So we resort to a model of a computation which makes this far easier. Okay? So that's why we consider NFAs. And we do this in math all the time. We have this model that is really hard to solve this problem, but we have this other model that's easier. So we try to link the two models together somehow. Any other questions? Yeah.
So you were saying like it's not really applicable in the real world, but then with maybe like a header and a user information, are you able to use NFA for that?
So you can't actually build an NFA, but like in terms of an actual machine, you can draw it obviously, or specify it. But we'll be describing a process to convert it back to a DFA. So once we make it, then we can implement it in the real world. So I can't directly make it, but it does have applications in actually making something useful. I think there was one more question somewhere. Any other questions? Yeah.
So you're pretty much saying, to simplify things, if I make this into a DFA, an NFA, then that means that you can make it into a DFA, which means it's regular?
Yeah, so by doing that, we'll establish that the NFA's languages are the regular languages. Mm-hmm. Exactly. And then we'll get the closure under concatenation and star for free based off of that, once we do it. Yeah.
So the NFA will take all the possible paths, but first it will take...
No, the NFA itself will only make one choice at every step, just like a DFA does.
But what if the selected path doesn't go into accept state?
So that if the selected path doesn't actually go to an accept state, that meant no path does, because that's what non-determinism means. If there is a path that does go to acceptance at some point, you will choose that. That's what non-determinism guarantees you.
What if there are multiple accept paths and we take the first one and we...
It'll just pick one. We don't know necessarily which one it'll pick, but if there are multiple that lead to acceptance, it'll pick one.
So if it doesn't accept in the first path, would be the case that it accepted it to the second path?
It'll always choose the second one in that case. If there is any choice that leads to acceptance, it'll make that choice, whatever that choice that is. So it's a magical choice selector.
There is no parallelism.
There's no parallelism with simulating it in an NFA setting. If I want to simulate it deterministically, then I have to do parallelism, yes. Because I don't know which choice is going to work. Did you have a question? Okay, other questions? Okay, so let's actually do this formally. So what we'll show is that we can convert. So this is definitely a formal description of a theorem. Can convert any NFA to an equivalent DFA. And by equivalent here, I mean they have the same language. And if we can show this, then we're all set in getting the closure results that we wanted before. Okay, so how in the world are we going to prove this? Well, let's see. So if I can give you an algorithm, say, I present to you an NFA, and the algorithm makes the DFA, is that all we need? So if I give you an algorithm to actually convert the NFA to a DFA, is this all we need? Yeah, that's all we need. Cool. So let's actually consider an NFA. So let M be an NFA with Q sigma delta Q0F. So states Q, input alphabet, transition, start state, final states. So no problem. Here we have an NFA right here. I want to actually make a DFA out of this thing. Well, let's see. Well, at each point right here, in our simulation here, could we possibly be in no states at a given point of the NFA? Is there a place where we can get stuck in our computation and not be able to proceed any further? Yeah, so like the Q0 reading a 1 example, there's nowhere to go. So for some places, I could have a choice that is bad and gives me 0 states out of it. Well, what about the other case? Could I go to all of the states, possibly? So I can be in all states via some choices that I made. Could I possibly do that? Maybe not with this example, but in principle I could. Could I go to any subset of states, possibly? Well, let's see. Well, at this point right here, the one before we read anything, what is the set of states that I can reach before I've read anything? What is the set of states I can go to without reading a single anything? Just Q0 and Q1. So those are the states I can reach right here. What about right here? After we've read the 1, what is the set of states that I can reach after reading a 1? Just Q2. Remember? So this is just a set of states. So the states that I can reach is just Q2 only. And at the end, we again have Q0, Q1. Oh, wait a second. So what does this tell us right here? It tells us, well, if you're in either Q0 or Q1, and you read a 1, the only state you could ever eventually get to is Q2. That's the only place you can go. Well, from Q2 reading a 0, you can go to these two states, Q0, Q1. Do you think that has some kind of relation on how we should make a deterministic machine? What if we made the sets of states right here, the Q0, Q1, and Q2, what if we made those as states? What if we did something like this? Let's just keep it up here, I guess. What if we did Q0, Q1 as a state itself? And we made Q2 a state itself. Well, how would I relate these two states together based on our computation that we did? Yeah, so reading a 1 from the top one would come down here. And reading a 0 from the Q2 state will go back up here. So does the name of the state in the DFA matter? The actual name of the state? No. But do you think it serves a purpose by labeling it like this? Yeah. How did we know to accept at the end? Oh, we had a path that led to Q1. Well, we had another path that led to Q0, and Q0 is not final. Why did we accept here? Well, is there some path that led to acceptance? Yeah. Well, in this, just look at the states now, the Q0, Q1, Q2 states up on the right. Which of those two states should be final? So remember, the name of the state says these are the states you could reach at this point. Well, if I can reach Q2, does that mean I should accept? No, it doesn't mean I should accept. So Q2 does not should not be final. What about Q0, Q1? Should that be final? Yeah, because at least one of the states is a final state from the NFA. Because Q1 was final, that means that this whole state must be final. Okay? What state of these two should be the start state? Q0, Q1, because Q0 was the start state before, so Q0 really should be the start state, but we're going to actually have to do something about this epsilon business. So in fact, Q0, Q1 is the start state here. Is this a complete DFA? No, what is missing? Well, the 0 from the Q0, Q1 thing. And so what would it be in that case? Well, what would a Q0, Q1 go? So from Q0 only, just ignore the epsilon transition, just Q0, where can I go on input 0? Just go to Q2. So I'm going to maintain a list of what we can reach so far. So we can reach Q2, that's fine. From Q1, where can I reach from input 0? Let's see. Well, I can reach Q1. Oh, sorry, I'm not paying attention. So I can only reach Q2. Have we made that state already? Yeah, so in fact, we can just put a 0 on this transition and we're done with that part. Are we done making a full DFA now? No, so what else do we need to do? Yeah, what does the Q2 transition do on 1? It stays there. Because why? Well, Q2 can only reach itself on input 1. Can Q2 go anywhere else on epsilon transitions? No. So in fact, we're stuck at just Q2. So in fact, this is a full DFA once we put that final state on. So the NFA on the left and the DFA on the right have the same language because we're simulating the NFA in all possible ways at the same time. Because we're only concerned about at least one path leading to acceptance. Okay, well, how many subsets of 3 states are there? If I have 3 states, how many subsets are possible? 8. I only have 2 states here. What happened to the other 6? They're not possible, right? So from the DFA here, we considered all possible things we could do, and we basically closed the branches, so to speak. So there's nothing else we need to do for the DFA, so they're not reachable. So the other 6 configurations, the other 6 subsets, we can't actually access those subsets. But could we possibly access all of them in the general case? Not just this example, but could we do all possible subsets, possibly? Okay, well, let's actually consider that when we do our conversion in the general case. So let's actually construct a DFA, D for Dougherty, obviously, Q prime, sigma, so the same input alphabet, different transition, different start state, different final states. Well, what are the states of the DFA going to be here? So I don't know whether some of the subsets are not going to work. So we might as well just put all of them in. Even if they don't work, we might as well put them in. Yeah.
What's the final state or initial state of both the NFA and DFA would be same?
Yeah, I'll address that eventually. You have a good point. Wouldn't the start state of the DFA over here be the same? But remember, the DFA doesn't have epsilon transitions. So we need to be able to include anywhere you could reach in the NFA via epsilon transitions because the DFA doesn't have them. So it's like you could have started in any of the states you could have reached via epsilon transitions. So we'll handle that business in a bit, but we're going to ignore it for now, conveniently. Okay, well, I don't know if some of the subsets won't work. So how do I say, well, any of the subsets of states could work? Someone said it. Power set. What if we just said the power set of the NFA states? Would that work? Well, that's kind of what we're doing up here. We're just having all the subsets of the NFA as states in the DFA. So the Q0, Q1 subset, that's a state in the DFA. The Q2 subset, that's a state in the DFA. Do you think the DFA will have a state labeled empty set? Is the empty set a subset of the state set? Yeah, it's a subset of everything. So, yeah, so all possible subsets that you could reach will be in here. What about the start state? So, conveniently, we're going to ignore the epsilon transitions for now. Well, the states in the DFA are what in the NFA? The states in the DFA are modeling what in the NFA? Not quite. What's sorry? Yeah. So each of the DFA states is corresponding to a set of states in the NFA. Well, the DFA state, the Q0 prime here, the state in the DFA, what is it going to correspond to in the NFA? A what of states? A set of states. So we better write down a set of states. Well, what should be in this set? Or what should definitely be in this set? The start state of the NFA, which is Q0 in this case. You notice I left a little room between the equals and the curly bracket. I'm going to address that. because we have these epsilon transitions. We'll deal with that later. Okay, well, let's see. Let's do final states, because the transition function, like always, is the hardest thing. So let's leave the hardest thing to last. The final states, remember, is a set of states. The final states are always a set of states, so that's always true. Well, how did we, from the DFA up here, the Q0, Q1 state, how did we know that was final? How did we mark that final before? Yeah, because one of the elements inside of it was originally a final state in the NFA, namely Q1. I didn't care about Q0. Q1 was a final state before. So you can think of this as saying it's all the subsets such that they have non-empty intersection with the final states. So in other words, all the states in the DFA, if they have a Q1 anywhere inside of it, they are final. Because I could reach Q1, that means that it should be a final state in the DFA. Okay, so what do we do here? So it's all the subsets X of the set of states in the NFA. So let's be clear here. The Q right here in the set is the set of states in the NFA. The reason I'm doing this will be clear in a second. But it's all subsets such that X has non-empty intersection with the final states of the NFA. So what in the world did I just write? It's all subsets which correspond to states in the DFA, remember? DFA states are sets of states in the NFA. Again, if you repeat it to yourself 100 times, you're almost halfway there.
Can you clarify if that's F prime and if that is F prime too?
Oh, oops, you're right. F prime. My bad. F prime on the left means the final states in the DFA. The F on the inside, I do mean the NFA's final states. So what do we mean here? Is all the states in the DFA where one of the elements in that set was originally a final state in the NFA. And that's all we mean from that. So that means exactly what we wanted up here. There was one member, at least, of Q0, Q1, which was a final state before. That's all we mean. Any questions about those three parts? Okay, let's do transition function. In general, what does a transition function take as input? What two things? State and input symbol. What about epsilon? What are we making? A DFA. Should we do epsilon here? Good. So you're paying attention. So delta prime. So this is for the DFA. What are states in the DFA modeling in the NFA? Sets of states. So I'm actually going to use X here. So X, comma A. So if we have a particular subset X and the symbol A, we want to know where we can go in the NFA to make it correspond to a state in the DFA. Well, let's see. How did we know at the beginning, so on the left of this vertical bar, how did we know to go to Q0, Q1? How did that become the start state? In general. Yeah, ignore the epsilon here. Well, Q0 is the start state, but we have another state that we could have reached. Ignore the fact that it's an epsilon transition for now. There's another state we can reach. What did we do with these two things together? We had a set which had Q0 in it. We had another set which had Q1 in it. What did we do to those two sets? We unioned them together. What about the one for, after reading one. So the first one was empty set, and the other one was Q2. What did we do to those two? We had empty set here, and set containing Q2 over here. What did we do to those two? Union. What is anything union the empty set? The original set, right. So in fact, what we're doing here is we're looking at each of the elements inside this subset right here. So let's look at this subset right here. So we're looking at, hey, what does Q0 do on some symbol? Figure out where it goes, and then maintain a set of where we can go. Then we transition over to Q1. We ask, where can you go on the same symbol? And then union the results together. What if we had 10,000 states in this set? What would we do? We would look at each of them in turn. This state goes certain places, this state, and then all other 9,997 other states. And then we would just union them all together because we just need to maintain where we could go, okay? So in fact, all we need to do is just union all the results together. So what we're going to do is, well, X right here is a set of states, okay? So then, for that reason, we need to look at the union of every, let's do a different notation to make it easier to read. Let's look at a state Y in this set X. So each Y here is going to be each of the states in turn, figure out where to go for each individual Y, union the results together. Well, how can I figure out, I'm scrolling up for a reason, how can I figure out where Y, the state Y in the NFA went on the symbol A? How can I figure out where it went? Look at what transition function? The NFAs one, which is called what in this case? Yeah, it's delta of, so delta is the NFA one. So here it would be YA. Excellent. So all we're doing is we're just simulating the NFA deterministically. We're just looking at all possibilities that you could reach in one transition, make a set out of all those states, and then make the transition in the DFA go to that subset of states. Are we done? Again, you can tell by my tone it isn't. What are we forgetting? The what kind of transition? Epsilon. And in fact, we've left it out in a few places. First off, the new start state here doesn't incorporate that because we said that right here, the start state is the set containing just a single state, whereas before, we had the start state containing two things. And we left it out of the transition function where we just said we just look at the states you can reach via the character read, but ignored the epsilon transitions afterward. So what are we going to do? Well, what we should do is figure out where we can reach via only epsilon transitions. So look at the example right here on the left. Where can I reach from Q2 via only epsilon transitions or not applying any at all? Well, what state can I definitely reach from Q2 without doing anything? Yeah, Q2 only. Can I reach anywhere else? No. So what about, say, just from Q0 only? Where can I reach from epsilon transitions or not doing anything at all? Q0 or Q1. So it's what we term this as to mean is we're trying to take a closure of something. We're trying to go as far as we possibly can, spread our wings as far as we can go, while doing some action, which in this case is only doing epsilon transitions. We don't want to actually read. So that's what we're going to define right now is the epsilon closure of a set of states, states X is the smallest subset Y such that the following occurs. Well, no matter what happens, if we have a set of states and there's no epsilon transitions we could apply from only those states, well, we better just be able to get to these states only, right? We want to include the states that we're already in. So we better have that X is a subset of Y. So Y includes everything we could already reach. So the epsilon closure of a set of states always includes the original set itself. But it might include other things. A small subset Y such that if there is a transition, I should say epsilon transition, where we have some state Q having an epsilon transition to state Q prime, where Q is in X, Q prime is in, is not in X, then Q prime is in Y. Yeah, I think that's fine. Making this up as we go. Kidding. So what does this mean? This says that we have a set of states right here. And let's just say that an epsilon transition is poking its head outside of this set. Well, could we reach the state that's immediately outside of that set? Could we reach it by only epsilon transitions? So let's just say we have this situation where we have a bunch of states in here, and we have one state on the right here that has an epsilon transition. So this set is X. That we have this epsilon transition that goes to this state outside of the set. The epsilon closure says we're going to include that state in the set Y. So we're building up where we can reach from X via only epsilon transitions. Okay. Could we have a situation where I have a state out here that has an epsilon transition on the way in? Should I include the outer state here? No, because the state from the tail of the transition wasn't originally in our set, so we do not necessarily can reach the outer state. We can reach the inner one, but not necessarily the outer one. But if we have a transition that goes outside, we can definitely reach the other one. And we will denote this by the E of X. So it's the E on the front means epsilon closure of X. So in the example we had before, the epsilon closure of just Q2 is just Q2. The epsilon closure of just Q0 is the set Q0, Q1, because we just include everything else we can reach and keep building until we can't anymore. Any questions about this? Okay, so we're almost done, I promise. No jokes. So what about our construction of our DFA? What do we need to amend here? Let's start with the start state. What do we need to amend to that? Yeah, epsilon closure, because if I start in the start state of the NFA, I might have epsilon transitions poking out, and I might be able to take those. So we should put epsilon closure on the front, because we just start in Q0 and figure out where else we can reach. Okay, well, the final states are okay because that's just a determination of whether a state is final or not. So the only thing we need to really change then is the transition function. Well, the way that we did it is we applied a transition, a character reading transition, and then we asked, can we reach anywhere else via epsilon transitions? So what we need to do then is put a E on the front and wrap this whole thing on the inside. So all we're asking is figure out everything you can reach via a single character transition, and then once you have that set of states, figure out anywhere else you could reach. Any questions about that? We're going to do an example, I promise. Yeah.
Shouldn't we also do epsilon closure on X?
No, I don't, because it's just the only thing that we needed to know from the NFA's perspective is whether one of these states is final. So I only need to know what the states actually are. I don't need to figure out what things I can reach via epsilon transition.
But in the delta function.
In the what part?
Delta prime.
Yeah, delta prime, yeah.
So we are only taking the states X, but shouldn't we take the epsilon closure of X?
Oh, okay, so what you're asking essentially, so I'm convoluting what you're going to say. Don't you love when a speaker does that? What happens is, what we're doing is we're applying the transition, then doing the epsilon stuff. Whereas what you're saying is, do the epsilon stuff, then apply the transition. Okay, is that what you're saying? So these two differences are, they pretty much are the same, essentially. But you can actually create an example where doing the second one is not the right way and the first one is correct. But to give you an idea of why that's wrong, the reason why we do it in this order is because of the start state. Because we do epsilon there, so we figure out where we can go from the start state on epsilon. But then if we did epsilon first and then the transition, then once we do the epsilon closure of the start state, we're already done. We can't go any further anyway. So the epsilon step wouldn't actually do anything for us. So we need to do it in the character then epsilon transition order, not the other way around, because of the start state. But I understand that it seems like you can do one over the other, but you can actually create an example where the other order is not the right way.
And what if we apply to the both epsilon closure on the first part and then second also?
Oh, so you mean like the X down here? So he's asking, why don't you apply epsilon closure down here? And the reason is, if you apply epsilon closure right here, it's not the right order because you're doing epsilon closure first, but it doesn't actually really matter. So I guess you could do it, but there's no real purpose because once we go to that state, we've already applied epsilon closure to get to there anyway. So in like the previous transition or at the start, we applied epsilon closure to begin with. So applying it again won't do anything.
I'm saying we have set of states X and we apply epsilon closure, then consume a character, and then apply epsilon closure again.
Okay, so what I think you're saying is this. Apply, yeah. So there's actually no difference here. So it won't actually make a difference. So this is asking, apply a transition, figure out where you can go here. transition, figure out where you can go here, etc. And then once I have this big tree of where I can go, figure out where else I can go. But you can see that I've already expanded each part as far as I can go anyway. So it actually won't make a difference here. I do need the outer one, but the inner one, I guess, is redundant. It's not necessary. I want to get into an example unless there are other questions. Okay, let's do an example because I'm sure we're all dying for one. All right, so let's do this one. Oh, and by the way, what does this prove about closure under concatenation and star?
It's also regular.
Yeah, irregular languages are closed under concat and star. And there's actually a name for this construction. It's called the Powerset Construction. I should have mentioned that earlier. And you may wonder why it's called Powerset, because we're taking the power set of the set of states. Like the product construction did the Cartesian product, we're doing Powerset. Yeah.
This also shows that NFA is close and regular.
That they recognize the regular languages.
Yeah.
So DFAs and NFAs are that they recognize the same languages.
Yeah,
Yeah,
they're equivalent.
yeah, they're equivalent power. Yep.
Using the Powerset construction as the first one
I can't hear you.
that Powerset construction first one added the parentheses.
Including the e's, and not the last one because it's not actually how Sipser does it. But as this, yes.
Okay, those are the Powerset.
Yeah, that's the whole construction. Suppose that my my NFA has 10,000 states. Okay, how many states will my DFA have? How many? If I have n elements in a set, how big is the power set? 2 to the n. So how many states would my DFA have? 2 to the power 10,000. Do you think I want to make a DFA that big? Hell no. Okay? So I'm going to actually show you a much better way to make our DFAs so that we don't make any redundant states or inaccessible states, I guess. So let's do this example. B back here. Let's make this more interesting. Okay. Yeah, I think that's okay. I'm trying to visualize how many states we'll actually need, and I don't think it's that many. If it's too many, we'll run out of time. All right. So we need to be able to make a DFA. So this is the NFA. We want to make a DFA for the same language. So how do I make the start state of the DFA here? Epsilon closure of the start state, which is what in this case? Q0, Q1, because I can't get anywhere else with epsilon closure. So I'm going to make the set Q0, Q1 be a state, the start state. Let's just say the characters in the alphabet are A and B. So where can I go from Q0, Q1? Let's make it simple. On B. Where can I go on B? Nowhere. Oh, what's that state going to be? Ooh, empty set. Anyone else that excited about the empty set? I'm excited about the empty set. I mean, it's just a state name. What should the empty set state do on A and B? Just loop, right? And should it be final? No, it shouldn't be final. Cool. So one of the only joys in my life in teaching this class is when you do the transition here and completely close it off and not have to think about it anymore. So the B path is done. Are we done making the DFA? No. So what else do we need to do? We need to do the A transition. Well, where can I go from Q0 on A? Nowhere. Cool. What about Q1? Where can we go on A? Q2 and Q3. So that's the set of states I'm going to write down so far. Can I get anywhere else from Q2 and Q3 via epsilon transitions? No, I can't get anywhere. Cool. So that's the set of states that I have now. Okay, so what about, so now we got to deal with the 2-3 state right here. Where can we go on input A from 2 and 3? Where can Q2 go on A? Nowhere. Q3 on A? Nowhere. Oh, what state is that? Empty set. Isn't it nice when the paths just come back to states you already made? What about the B transition? Where does Q2 go on B? Q2 and? Q0. We'll deal with that in a second. Let's see. Can Q3 go anywhere on B? No. Here's an important question. What is the epsilon closure of 0 and 2? Where else can I go from those two states only on epsilon? Q1 via from Q0 and 3 from 2. So I better include those states as well. Okay, great. What about on B for this monstrous state? What about on B? Where does it go? Well, this set includes 2 and 3. So doesn't it go to all states? Ah, so that's easy. So this loops on B because 2 and 3 get to all the states, so I don't really care about what 0 and 1 do because I'm just unioning everything. But what about on A? Well, where does 0 go on A? Nowhere. Great. 1 on A. So 2 and 3. Oops. 2 and 3 so far. Where else can we go? What about Q2 on A? Where does it go? Nowhere. 3 on A. Where does it go? Nowhere. So what is the epsilon closure of 2 and 3? Can I get anywhere else from 2 and 3 to anywhere else? No. Oh, do we have a state already called 2, 3? Ah, yes. So in fact, we can close off all paths like this. Is the DFA done? No, what is left? Final states. Which ones are the final states? Anything containing Q3. So 0 and 1, definitely not. Empty set, should that one be final? No. Does it contain Q3? No. Good. So 2 and 3 definitely is. And certainly the one that has all states. And Geico and, yeah, AAA. Anyway, cool. So, in fact, we can make, so how many states could I have made if there are 4 states in the NFA? 2 to the 4, which is 16. The other 12 states are completely unreachable. Isn't this a lot easier, building the states as you go? Cool. I'll see you next time.